So welcome to our final session for Aviation in the Pandemic, Aviation in the Pandemic 2. My name is Shannon Zielinski. I work for NASA Ames. I'm a branch chief in the Aviation Systems Division, which specializes in air traffic management research. We have two really interesting papers for this half of the session. Just as a reminder, please enter your questions in the Q&A chat at any time during the presentation or after so that we can get those asked in a timely manner. So our first paper is an online platform for the short-term prediction of risk and expansion of epidemics. This is presented by Javier. Javier Garcia Moreno works in CRIDA, the Spanish Reference Center for Research and Development in Air Traffic Management in Spain. And he has a Master's of Science in Aeronautical Engineering, specializing in air traffic systems. Currently, he is a technical developer of research and development projects in the field of aviation and U-space. So thank you, Javier, and please begin.
Hello, good afternoon. Thank you for the presentation, Shannon. Good afternoon in Europe, good morning in the USA. Thank you for this introduction. Today I'm going to present you our work, which is titled the Online Platform for the Short-Term Prediction of Risk of Expansion of Epidemics. And then I will show you this platform with a proof of concept based on the COVID-19 evolution. I also want to thank the co-authors of these works, my colleagues from CRIDA, the UPM, and also from the Northwestern University. Okay, so this is the structure I'm going to present to you today. First, we're going to review the scope and objectives of this project. After that, we're going to review the methodology of our import risk indicator and the validation process we are following. Later on, we will show you some results of our proof of concept based on the COVID-19. And to close, we will talk a little bit about the conclusion and future plans and expected benefits. Okay, so let's begin about the scope of and the objectives of this project. So I think we all know how the COVID-19 pandemic has affected the aviation industry. Where probably mid-March, February, all countries in the world started to apply some really restrictive mitigation measures to contain the spread of the virus. That was something really new for us. And I think that at that time, there was some studies indicating that the air transport network was one of the main ways the virus spread that fast around the globe. And also that in the future we will face similar problems, no? Like all the virus, all the pandemics. We are seeing like now we are seeing different COVID-19 variants that are really affecting, no? And as well other emergency that could be spread, no, through the air traffic network. So based on that, we were thinking how as a research company based mainly on aviation could help society and aviation industry during these hard times. So we were in contact with the NAIRE, which is the Spanish air navigation service provider, and through the ideas lab, we were proposing different solutions. No, one of them was the development of an application or a platform that was able, no, to predict the level of risk of an epidemic, in this case the COVID-19, propagating through the air transport network. And in fact, we wanted to determine which elements in the network, like for example, airports, airlines, routes, even specific flights, no, have a major contribution, and also which mitigation measures can be applied, no, for the different countries to be more efficient in the contention of the spread of the virus, and also not to really affect, no, the aviation industry. This is more or less a global issue that we were thinking a solution at a global scale as well. But this topic was certainly new for us. And that's the reason we needed to create a multidisciplinary team, which was composed not only from us and the Spanish air navigation service provider, but also from top universities in Spain specialized in aeronautics and software development at the University of Madrid and the University of Barcelona. But in addition to that other relevant industry we wanted to take on board was the health industry. No, we were in contact with the Medicine University of Northwestern University in Chicago, in the US, and also from the hospital of Vall d'Hebron, placed in Barcelona. No? And together we started to develop this project, which is, I must say, is constantly evolving and being improved, because we're seeing the potential, no, of this project. Okay, now explain the ground. I will explain more or less our main, let's say, produce. No, it is the import risk, its methodology, and also some validation process. So the main idea was to develop an indicator that was able to reflect the probability of a flight, let's say K, transporting infected passengers from an airport I to an airport J. So we came out with this, what we call the import risk indicator, where it indicates the probability as the probability of a passenger having the disease, in this case COVID-19, on a flight K. No? And this, the probability is expressed as the corrective factor, no, based on some hypotheses multiplied by the infected people in the influence zone of the airport in the last 7 days. We choose 7 days because 7 days is the contagion period of the COVID-19, and we divide it by the total population in the airport zone. We also, taking into account the health industry, we were computing as well the evolution of the disease in flight, so the evolution of the virus on board of the airplane, and in addition, we wanted to know how it evolves, no, during the different flight phases, because it's not the same a short flight like rather than a long range flight. To compute this evolution of the disease, we were using the SEER methodology, which is a methodology that is quite spread used in the health industry, which is called the susceptible, infected, and recovered people. Okay, but there's also some factors, no, that evolves or depend along the time, no. And especially it depends on the kind of virus, no. It's not the same the flu than the COVID-19 or so on, no. There's specific parameters that are closely related to this disease. That is the alpha and beta parameters, which are the infection rate, which is the probability of an infection in a population, and also the recovered rate, no, which is the proportion of the infected people recovered per day. Those parameters are really taken into account into this SEER methodology, where the susceptible people to get infected need to take into account the flight duration and what is the probability, no, of getting infected through the COVID inside the aircraft. Okay, so after computing this risk indicator for every flight K by an airport J on a given day, we conclude that the sum of the risk, no, of each flight from all airports I with operation on that day is our imported risk indicator for some specific airport in the world. Okay, now we have more or less described our indicator, but are we able to predict the evolution of infected people in a country or in a certain airport by exploiting these indicators? This was one of the main questions we were asking, and to try to answer this, we developed some validation methodology in order to try to compare our indicator, no, to test how good it is. So first of all, we were computing this indicator for all flights in the world, which were departing or arriving in any airport. And also the other indicator we were computing was the amount of infected people in that airport areas, no? And we divided into actual infected in the actual day, and also in order to see the correlation in the future, we compute the accumulated infected people for the actual day to 50 and 30 days after the computation day. After that, we were proceeding with a filtering and data cleaning process, in order to detect some outliers. We were using the Mahalanobis distance and chi-square to filter some outlier values that were below the 97.5% quantile. We also have performed a principal component analysis and a cluster means to observe if there are contents with a similar behavior, and if so, try to evaluate them separately. And then the next step, we have performed a logarithmic transformation just in order to perform, to better represent these results in a graph or in a chart that we are going to see later. Finally, what are we going to do in this validation methodology is to compute some correlator indicators that shows the relationship between the two variables. In this case, our import risk indicator that I have just explained, and also the amount of infected people, the infected people in the actual day, and also the accumulated for the following 15 and 30 days. We compute 3 different correlation indicators in order to make sure they are all coherent, the results that we're computing. So we choose the Pearson, Spearman, and Kendall-Tau one. Finally, when all of these correlation indicators are computed, we are going to represent them in a box plot with the correlation indicators for all periods that we analyzed. And we are going to select the median value of the box plot. If at least 2 of the correlation indicators are above 0.5, we can say that, okay, our hypothesis and our indicator is working correctly. Nevertheless, if there's only one correlation indicator above 0.5, probably there's something else that we need to explore. And if none of the correlation indicator is above 0.5, probably our indicator is not really useful, okay? Okay, now I'm going to show you the results of this platform, based on the COVID-19 disease. The results are structured like this one. First of all, I'm going to show you our online platform as a web-based application that we have developed, and all the characteristics of this application. And secondly, I'm going to show you some results of the analysis of this import risk indicator, where we have explored 2 use cases. First, at a worldwide scale, a second one at the Spanish level. Okay, so first of all, our application is based on real data. We gather data from let's say two different worlds. The first one was from the air transport network at a worldwide scale. For that purpose, we choose to use information from Flight Radar 24, which is a company that provides ADS-B information from Flight Radar from almost all flights around the world. This data contains information about the departure, arrival times, departure and landing airports, aircraft types, and so on. Then we also use some information from the IATA, especially occupation factors per continent and month, to see how busy were the flights in those days. After that, we selected some real data from the emergency and epidemic information and its evolution from the Johns Hopkins database, which mainly contains the information in the SEER model, the susceptible, the infected, and the recovered persons, in the different areas. Our platform is automatized to obtain new data periodically. So this is executed every day in order to obtain new information about the flights of one day, the status of the disease from the Johns Hopkins, and so on. And with this information, what we did was to model the air transport network as a graph. We use a tag graph. I'm going to show you later. When we compute our risk indicator for all flights, and we included these characteristics. So our tag graph is the structure look like this. On the left part of this graph, there's the aeronautical more information. So it's the airport on one specific day and all the flights related to that airport, all the departures and landings. And on the right side, we have all the reports that were coming from the Johns Hopkins and were linked to the regions or the different countries and influence areas of the airport. Okay, so this was mainly the way we use to construct our graph database. The main result of this graph database was the interactive user interface to be part of this web platform that we developed, that can be used to analyze in real time the actual situations and also future scenarios. I have provided here the link. I think we won't have time to go into a live demo today. You have also the link in the paper in case you want to explore a little bit. I just put here some examples on the platform. I just extracted some days from the beginning of the pandemic. So the colors in the maps, well, this is a common result from the application. The colors in the map, as you can see, represents the amount of people infected by COVID-19 virus. If it's more purple, it represents that more people is infected in that country. While on the other side, we have also some bubbles that represents the airport. The size of the bubble represents our import risk indicator. If the bubble is big, it means that the airport has a high imported risk indicator value, and so on, a high probability on develop in the future more COVID cases. In this picture, you can see that this was in February. We can see that China was in color purple. And we can see that at that time, the size of the bubbles in Europe were starting growing, And you can see that, for example, in Africa, South America, or even in the US, the size of the bubbles were not really big. If we compare that scenario with 2 weeks later, we can see that China was still being the #1 in infected people. But at that moment, I think it was around the beginning of March, Italy started to have the first contagion numbers. And you can see clearly here that the size of the bubbles were continue growing in Europe. The import risk to obtain this disease was increasing. And we can see now that the US is starting to appear as well in our import risk indicator, and some airports, some bubbles are growing in size, Finally, 2 weeks later, both the US and also Europe were starting to having many cases of COVID. The bubbles of the airports in China or in Asia, we can see that are now disappearing, indicating that the most or the import risk for those countries in Asia are not that relevant in that time compared with the US and Europe, This is one of the examples of the studies that this platform allows to do. More characteristic about this application is that we can export all this information into several formats and files with the interactive table format functionality, where we can see the top risk elements in this network. Like, for example, which are the top countries in the world that has the most probability of export this disease. We can even go into deeper details onto some airports specific routes, to see if, for example, there's any connection with any flight that probably has a high risk to import into your airport some passengers infected, And even we can target the specific flights, Probably there's some flights that were more dangerous than any others, These are more or less the characteristics that we are trying to see in order to develop specific measures, Because at the end, what we want to see is, okay, we are now seeing how is the the risk for some of these elements in the network, and can we do something in those elements in order to provide a specific, or let's say more efficient measures, no, rather than close the entire airspace or just ban flights from specific countries or continents, no? For that reason, we developed, or we included these what if functionality measures. So that means there is a functionality that allow us to test what would happen if we modify some elements, no, in the network. There's two things that the user can modify in this platform. The first one are the elements in the air transport network, like, for example, airports, routes, airlines, specific aircrafts. No, the user can select for a specific day what would happen if we modify one of those elements. No, like imagine if we restrict all flights from, let's say, China, no, or from a specific airport from, let's say, Japan. No, so the user can do that as well. The other thing that the user can modify is to modify the parameters of the emergency or the epidemic situation. No, I was talking before that this risk indicator that we have developed is highly dependent on some variables that depends on the virus. No, these alpha and these beta parameters. So what would happen if, for example, there is a new disease, no, or a new variant of this disease, no? Then the user is also able to select a specific country, a specific situations in order to change these SIR parameters in order to compute again, no, what's this kind of risks. Okay, that was partly the web app application, the platform. Then we use this platform in order to extract some values to test how good was our import risk indicator. Okay, so in this chart you can see the correlation indicator for the import risk versus the infected people up to that day. Also 15 days after, the accumulated people that was infected from that day to 15 days later, and also the same but for 30 days later. No, these results are at a worldwide level for a period of the first 4 months, no, of the pandemic. And we can see here that the results that we obtained for a linear correlation, the results were all above the 0.5 level that we have defined before. And the performance showed here was even better than expected. No, we can see that even 30 days after, the correlation of this indicator is around or close to 0.7. If we look at this result at the linear or date scale, we can see that these indicators are more or less showing a stable correlation. No, probably at the beginning or 1st of February in 2020, we can see a decrease on this correlation on the first day, but after that the correlation turns, let's say, stable. Okay, and what about the rest of indicators of correlation that I was talking before? So we computed this one from Lineal, Spearman, and also Kendall-Tau correlation indicators, and we saw that all correlation indicators were showing good performance of above 0.5 that was determined before, even in the medium and long term. No,
5 minutes remaining.
Okay, thank you. So we tested this application as well with the use case of the Spanish use case. And we can see that here, for example, in the top chart, we have the evolution of our import risk indicator, and in this point, we selected how Spain was in the world ranking, no, of imported risk. We can see that it was at the end of February, around 23rd of February, Spain has only 2 infected people, but at that moment was at the number 17th in the world ranking for the import risk indicator. 2 weeks later, Spain has started to have a lot of infected people, but there was not too many, like around 600 people. But at that moment, Spain was in the number 3, no, in the world ranking. 15 days later, of course, Spain started to have more than 30,000 infected people. No, so we can see here that the import risk indicator is alerting, no, like 10 to 15 days before having the first positive cases in Spain. Also, the correlation was showing a good performance for 15 and 30 days, around 0.89 and 0.8 respectively, and some validation conclusions. No, the first one is that our import risk indicator is showing a good correlation performance to describe the evolution of the spread of the disease, in this case, the COVID, for 15 and also 30 days later. Of course, local measures are different in every country, so implying that the result shows different correlations if you go to the platform to analyze specific countries or airports, and probably this is due for the local measures. We have selected or analyzed different alternative measures, no, with the tool, but then an optimization criteria to select the best option was not really yet validated. The platform can be used to predict new COVID-19 variants, as I was using. No? So what are the future plans, no, and the expected benefits of this platform? So, okay, based on the good results that we have obtained from this proof of concept to predict the evolution of the COVID-19 for each country, we think that we need to continue to develop this application, no, to predict systematically the expansion of the future epidemics, no, or any other emergency situation. And we need to analyze these local mitigation measures and to think at a global scale, no, because this is a global problem that probably needs a global mitigation measures and need to be coordinated between them. The expected benefits of this platform is to monitoring the capacity and the prediction of future pandemics or emergency situations that, of course, expands through the air transport network. And this application of the measurements of efficiently based on the risk of expansion, no, and its causes, in order to reduce the economic impact of the applied measures. There are some future improvements that are set closely to be produced, like, for example, to include the transfer passengers, no, to see if, okay, we apply the measure which is ban or restrict flights from a certain country, but at the end there's passengers that are flying through connections, no, through other countries, and they are arriving to your own country. Also, we want to include the risk of the local contagious inside airports and improve our local contagious inside aircrafts. We would like to have these parameter settings of the essential characteristics of some epidemics, and also the identification of these predefined air traffic related measures, no, with the decision makers, which are the end the ones that develop these capabilities, no, these measures. Of course, all this solution, we pretend to do a large project to mature this solution in Horizon Europe, which is being under development. And that was all from my side. Thank you very much for attending, and this is my contact if you have any question.
Thank you, Javier. I think we're still awaiting questions in the chat, unless I can't see them. I was kicked out of Zoom for a second and resumed. But I guess while I'm waiting, I have a question. I was intrigued by your next steps, because currently your what if capability allows you to play with the transport network elements and the health emergency situation, but you mentioned that this tool could have also be helped to inform mitigation strategies, and I wonder if those could extend to the local area, because say the imported risk coming in, but the imported risk of the area is not quite yet bad yet, but you can see the imported risk of all the other connected areas coming in is going to increase your risk. And so perhaps then the city would say, okay, maybe we should all wear masks again in public, or the restaurants should have the indoor mask law or something like that. If you had any thought as to modeling mitigation strategies that are more local like that, and how they would play in your what if model?
Yes, that's a really good question. And this is something that we are concerned, and that's why we want to, let's say, to talk with the decision makers, no? Because at the end, the local measures are really relevant, and we are seeing, I think there was an indicator from a website which is identifying those local measures, where are applied at which time. And maybe we are planning to use this information in the future in order to see how specific measures, like for example wearing masks or being vaccinated, and so on, how this is affecting at the end to the spread of the disease after a long period of having those local measures taking place. So I think it is really relevant to do or to perform this coordination about the local decision makers as well, in order to propose measures that are not only restrictive to the air traffic or airspace management, but rather local measures like wearing mask or maintain the distance, the security distance, that probably are more effective than restrict some flight routes or some flights, or even closing the airspace.
Thank you. I still do not see questions in the chat. So I guess I'll ask, I saw earlier, so the earlier talk that we had, included other modes of transportation in there. Do you think that there's any room for including like imported risk via other modes of transportation?
Yes, of course. And this is one of the main things that we also want to improve. I saw the presentation of Lou that was including this traffic by road, no? And I think it's also quite relevant to include all these transportation modes, no? Because at the end, this is a disease that is spread through all the traffic network, not only air transportation. So of course we will need to include more transportation modes, like for example train or public and private transport is affecting the spread of the disease. And probably local measures and other measures can be applied in coherence with all these transportation modes.
Oh, here I have a question from Sandy. Are there particular data from local governments that would benefit your approach?
Well, yes, I think that, for example, we were talking about different transportation modes. For example, all the data about the public transportation, like for example, train, metro in big cities, bus, and this kind of information will be also relevant, to try to analyze in which stages different transportation modes are more relevant than others. Probably aviation is one of the biggest, one of the main sources of this spread at the earliest stages of the virus. But after you have local contagious, probably the air transportation is no longer that relevant, within the whole transportation network. So of course, the facilitation of this information and also the coordination with them will allow us to predict or to have better information, to proportionate these more relevant indicators.
Thank you. Cindy has a follow-up. What about the healthcare data?
The healthcare.
Healthcare data.
Yes, that will be also, I think, all kind of information. I think it will be valuable to add this information. Information about healthcare could be relevant, no? Because we have seen that not everybody is affected in the same way, no? We're seeing that probably elder people is suffering in a different way than young people. Here now we have in Europe this COVID-19 vaccination passport, no? All this information, I think it would be also relevant, no, to add into this analysis. In fact, this European vaccination passport could be one of the main measures, no, to be applied in some specific areas to contain the spread of the virus.
Great, thank you. I'm not seeing any further questions. I think this is an interesting approach. I hear because of all the variants coming in that this is transitioning from pandemic to endemic. So I'm sure there's much work still to be done in helping us all recover, or I guess reorient ourselves to the new norm. So if there are no further questions, I could thank our speaker and a virtual round of applause. And to stay on time, in case there are people jumping over from another session, we'll wait the 3 minutes until 20 after the hour. And welcome back to Aviation in the Pandemic Part 2. Our next paper is entitled Modeling Impacts of Aviation Mitigations and ATC Delay on Passenger COVID-19 Infection Risk. And this will be presented by Rich Delara, who's technical staff in the ATC Systems Group at MIT Lincoln Labs. For the past 20 plus years, he has focused on the analysis of complex systems and development of decision support in the air traffic and military operational medicine domains. So let us welcome Rich, and please take it away.
Hi, great. Thank you, Shannon, for the introduction, and thanks to all of you who have chosen to stick around for the very last talk of the conference, at least in the session rooms here. We will be talking about modeling the impacts of aviation mitigations and ATC delay on passenger COVID infection risk. I'd like to acknowledge Tom Reynolds, my co-author, who contributed significantly to this work. Okay, there we go. Any good talk should start with disclaimers. Here's ours. This material is based upon work supported by the United States Air Force. Any opinions, findings, conclusions, or recommendations expressed in this material are those of the authors and do not necessarily reflect the views of the United States Air Force. Now we can begin. We're all aware of the enormous impact of COVID-19 on pretty much every facet of our lives. Aviation was particularly hard hit. You can see from the plot here that domestic passengers screened by TSA fell to about 4% of 2019 levels early in the pandemic and began a rather robust recovery until probably the early fall, when the recovery stalled at about 40% of previous year as the disastrous third wave took effect. The robust recovery did not return until early March, when vaccines began to be deployed. That recovery has sort of plateaued again around 80% of 2019 levels, probably in part due to the emergence of the Delta variant, and we'll see where it goes. As this unfolded, stakeholders had to sort of respond on the fly, and they were flying blind. They had needs for transmission risk models in aviation. They had needs to understand the risk reward benefits of different mitigation options. They need to understand the impact of near-term response strategies, such as empty middle seats or restrictions on load capacities. And then there were longer term questions about structural changes. We've heard a little bit about the effects of networks, for instance, and visions of aviation for evolution to deal with public health issues as well. We are going to focus in this paper on the short term mitigations and needs. We have here sort of a very familiar set of aviation system relationships, certainly supply and demand, the effects of economics on demand, and the effects of public policy on the industry. And these are reasonably well understood, at least well enough understood for operations to plan and sustain themselves. However, we had a terrible uninvited guest who came along. COVID impacted all of these in severe ways and in ways that were very difficult to understand. All the stakeholders needed to come up with mitigations again on the fly. Airports control passenger density. They had to manage ventilation, mandate mask usage. Passengers had to make decisions. Should I fly? Should I not fly? What should I wear to protect myself when I fly? Who should I fly with? And the government also had to come up with public health rules and to provide stimulus money, perhaps to encourage good behavior. In order to make these kinds of decisions, though, you want some sense of the risk reward, the relative effectiveness of different strategies. And quite simply, you might, for aviation, want to say, all right, out of all the passengers, how many passengers I transport and how many will become infected in transit. And that's how I might evaluate a strategy. And that is sort of where we focused as we started to do this work. So our key questions here were, what are the relative risks of COVID-19 transmission in different environments? And we looked at the air departure gate waiting area versus the aircraft cabin. And what are the relative impacts of mitigation measures in each environment? You know, which measures are most effective at reducing transmission and which are most cost effective as well. We also looked at the impacts of operational performance on COVID-19 risk. You know, as we begin to return toward normal, we now are starting to see again ATC delay, certainly through the summer. And how does that affect transmission risk, particularly in the airport departure terminal? We know when you have a lot of delay, you get a lot more crowding. So what's going to happen when that occurs? We also want to know how robust those mitigations are to these kinds of disruptions. And of course, finally, underlying this whole thing, it's an environment of enormous uncertainty. We still lack a lot of ground truth data to guide our models and conclusions, and obviously a very complex system. So we'll review the sort of methodology, talk a little bit about the model and simulation, some results, and then summary next steps. So we took some inspiration from some work way back in the 80s on some scenario design methodology to frame our problem. And it was developed to help the oil industry plan very expensive and critical oil exploration decisions in the wake of the Arab oil embargoes of the 1970s. So focus on formulating strategies under deep uncertainty. And the approach is to use very coarse-grained models to identify the serious consequences and critical factors, and then use what you learn from those to focus your more detailed modeling on the critical system elements. We're also using some work from the 90s, talking about multi-scale modeling to guide scoping, resolution, validation. And the main story here is that create a model with resolution that's appropriate to your knowledge, uncertainty, your data precision and accuracy. Don't use a high resolution, high precision model if your data don't support it. However, where you can use higher resolution, you want to make sure that your low resolution and high resolution models are consistent across scales. So this gave us a sense of the framework to design a model that's appropriate to the challenges. We came up with something that's very fast, but also very approximate to enable a wide range of parameterization to deal with the uncertainty, and flexible architecture that enables rapid updates, because the information about the pandemic was changing daily through 2020 and continues to change quite rapidly. So there's our, let's talk about the context, where this model sits where this work will sit in the larger world. There's our familiar relationships disrupted by COVID. We're looking at aviation supply, and of course, there's a very high level strategic planning, long-term portion of determining aviation supply, but we are looking at near-term things, and that's really the door-to-door fine-grained operations. And this is sort of familiar phases of door-to-door flight, check-in, security, and so on. And as mentioned earlier, we're going to focus on the departure gate and in-flight portions, take operational parameters in, such as loading and environmental, indoor environment, and try and estimate new infections that will occur. Okay, let's look more detailed at the model. Again, the domain was the cabin and the gate, and the mitigations specifically are reducing passenger density in both environments, mask wearing, compliance and effectiveness, and then increasing air circulation. in particular the air removal rate, which I'll get to momentarily. The model really has the simulation really has two steps: an initialization to set up the environment and an exposure phase, and then eventually we post-process to roll up. The initialization, we start with sort of the external parameters, the prevalence of disease in the general population and in the traveling public, the infectiousness of the infected passengers who do travel, and the type of cabin. Are we talking about narrow body, wide body, whatever? Mitigations or loading rules in particular for the air cabin. How dense, empty middle seat, every other seat, caps on load factors. At the gates, we're looking at gate characteristics, particularly the area, to enable some level of social distancing. In the initialization step, then we generate our passenger list, who's infected, how infected they are, and we distribute them in space both on the aircraft and at the gate. Once that's done, we then go ahead and emit virus and expose people to it. The emission and exposure is really the same at both environments, the gate and the aircraft cabin. The controls are environmental controls, in particular the air removal rate, and masking enforcement and compliance. The other things, exposure duration, are set by the experiments. Virus deposition and inactivation rate are much smaller factors and are also set. What we come out with is the exposure level for passengers, infection probabilities, number of passengers transported, and we can use that to post-process to get our probabilities for comparison. So let's talk about that initialization phase. Prevalence, like I said, is a probability that an incoming passenger will be infected with COVID. We did not try to estimate this. We simply set this as a parameter that would come to us from some of the external work, similar to some of the things you've seen presented earlier in your work earlier in this session. Infectiousness was very challenging. It's a function of the individual's biology, the stage of infection, their activity. And there were no published estimates of sort of a distribution population of emission rate at any given particular time or in any particular population. There was some fine work sort of measuring sort of the range. There's a potential range of infectiousness of 100-fold, even 1,000-fold from some laboratory work. And we used that to guide us, but by and large, we were flying a bit blind. We selected a probability distribution that made possible the occasional rare super spreader event that was observed in case studies, but by and large led to a more, I guess, more default level of infection that was not too bad or not too good. Distribution of flight passengers is pretty straightforward. Randomly assign passengers to seats. The one important thing here is our assumption is that once assigned to seats, passengers did not move. So we were looking sort of for kind of general course grade, as I said, estimates here. And so one of the simplifying assumptions we made was that once passengers are assigned their locations, they stay put. Let's talk about the exposure and the transmission environment. We'll start with that infected individual who emits virus at a particular rate that's drawn from that infectiousness curve. That individual may be wearing a mask, and that mask is characterized by filtration efficiency, which is really three factors: the quality of the mask, the fit of the mask, and the compliance. Is the person wearing it 100% of the time, 50% of the time, whatever. So we rolled those up into a single number for estimation here. On the exposed side, the receiver, there's masking again that reduces the exposure. The dosage that susceptible person receives is a function of the concentration of virus in the atmosphere, the inhalation volume, how much air they breathe in, and the time of exposure. And again, set by our parameters, the duration of the flight, the time you're sitting there at the gate, and of course that filtration factor for the mask. You can derive the infection probability using a widely used equation, the Wells-Riley equation. It's an exponential. The probability of infection is an exponential function of dosage. In the environment itself, the biggest issue here is sort of the dispersion of airborne virus. And You can see some of the parameters there. We set a maximum dispersion distance, particularly important in the cabin because some of the computational fluid dynamics and the case studies seem to indicate that airborne virus is not likely to extend much more than 3 or so rows in front of and behind a given person. So they're sort of like little 7 or 8 row compartments there to which airborne virus transmission is restricted. So there's a fall off in concentration with distance as well. And there's a dispersion depth, which sort of represents the amount of the volume from which a person inhaling virus might draw the air, might draw a virus. We also have a dispersion angle, which is a proxy for the mixing in the environment. And in all cases here, we used a dispersion angle of 360 degrees. We didn't try to get clever about directional transport. Okay, let's look at the modeling results for aircraft gate and cabin mitigations. So we wanted to do 2 things. We wanted to look at the most effective airport gate mitigations, and we wanted to evaluate the effect of masking. So the mitigations we looked at were the area of the departure gate. We had a small gate, 150 square meters, and a large one, 300 square meters. In the results, they'll be coded respectively as red and blue lines, and that's the departure gate. We had 2 air removal rates, 4 per hour and 12 per hour, again, respectively downward and upward triangles. 12 per hour, I think, is roughly equivalent to what's recommended for a shopping mall. 4 is more like an auditorium. Interestingly enough, I could find no suggestions for what an aircraft terminal should be. So that's why I had to use proxies. Mask filtering, you can see no mask, low, moderate, and high. Remember, that's a combination of fit, quality, and compliance. And then we looked at 3 load factors, low, every other seat, empty middle seat, and high, 90%. The other factors were fixed, the cabin air replacement rate, 20 per hour, the duration at the gate, 60 minutes, 4-hour flight, 240 minutes, incoming prevalence of 1%, and that log normal emission rate distribution that you saw for infectiousness. Simulated 1,000 flights per factor level combination. So it's 48,000 flights, ran about 10 minutes on a little dull laptop. So we're at least meeting a performance requirement that we set for ourselves. So let's look at the first illustration, the airport gate mitigations. And if you look at the right there, you can see the curves, the blue curves for the large gate. And the red curves for the smaller gate, upward triangles for high air removal rate, downward triangles for low. And you can see both mitigations have significant impacts. The air removal rates getting you something on the order of, I don't know, maybe a 25–30% reduction in transmission probability at all aircraft load factors. And the increased area, doubling the area, is actually probably even a little bit more effective here by comparing the blue and red, at least if you're at low air removal rates. At high air removal rates, the reduction in transmission is about the same. By this model, the exposure both at the terminal and gate and inside the aircraft contribute to infection probability. Certainly all of these depends on the relative time spent in each place. And there may be other factors as well, but you can see they're both contributory factors. The overall probability is low, although again, our goal really is relative comparisons rather than absolute. And we can see there's nearly a 3 times increase in infection probability from our best case scenario, which is large gate area and higher removal rate, to our worst case scenario, which is a low gate area and a low removal rate. We took another approach here as well to look at masking. And what we did is let's say we set a sample target for infection risk of 0.2%, 2 in 1,000. And on the left, on the plot here, you can see that you can meet that target even at a 90% aircraft load factor, as long as you have masking filtration of 0.25 or greater. But that is with that 300 square meter gate and with that high air removal rate. If you look at the worst case, that 150 square meter gate and that low air removal rate, you can still meet that target infection risk if you increase your masking filtration effectiveness, if you double it from that 0.25 to 0.5. You can still meet your 90% aircraft load factor, meet your sample target simply by improving compliance and quality of masking. If you want a highly cost-effective way to reduce infection and maintain capacity, get a mask. Let's look at the impacts of ATC delay. So the goal here is, let's look at in the departure gate, and as we know, as we've experienced, as you get longer delays, gates become more crowded. So we fixed a bunch of factors here: prevalence, emission rate. We set the masking at filtration of 0.5, and we set the operation 20-hour schedule, 30 gates. We simulated 30 days of operation, 20,000 departing passengers per day. We looked at two load factors, assuming a 150-seat narrow body, an empty middle seat, which resulted in 200 flights to service the passenger demand, and 156 flights with a higher load factor of 85%. We assumed no aerosol transmission between the gates, and we created two delay profiles, moderate and severe, which you can see over there on the right. No delay, the flights go off as planned. Those are in 15-minute buckets. You can see the hours of operation across the x-axis. Moderate delay, you can see, and the severe delay impacts on how they distort the departure schedule. Okay. The simulation process, a little bit different, although the underlying models are the same. First, we create the departure gates and set the environment. That's the same as the previous simulation. We then create a flights per schedule block schedule. So we have a departing flight schedule. We generate a passenger list based on the load factors. And then we use an airport arrival distribution time. We made it up. We didn't have an opportunity to dig deeply in and find data from terminal operators. So we created one, and that gave us a distribution of arrival times for incoming passengers and also for the incoming infected passengers. Again, we assigned flights to gates so that we, by proxy, then assigned those arriving passengers to gates. And then we generated flight delays, and you can see we had two flight delay distributions, gave us actual schedule and actual departure times. And then for each scheduled block and each departure gate, we brought in the arriving passengers, emitted virus, exposed the susceptible passengers, removed the departing passengers, and then we tallied the results. What was the exposure for susceptible passengers, and eventually the roll up for the expected value for number of infections over the course of the day. Here are the results, and they quantify. The quantify was kind of obvious, right? Delays increase crowding, and crowding is going to increase infectious spread. One interesting thing here that's hinted at with these results is that the delays increase, the difference in infection counts between load factors seems to decrease. Where you have low density load factors, you have more flights occupying more gates, and more of those gates become crowded. So that's our working hypothesis, but validation of this is a challenge, and I think this needs to be explored with more robust and comprehensive simulation. The results here you can see quartiles, medians, and means, and you can see that the gap closing as the delays increase, as I suggest, but I don't think we had enough data here and enough comprehensive simulation to make significant statistical statements about the behaviors. The other thing that this was interesting and enabled us to do is to look at the intraday dynamics within the terminal. And you can see here, the demand profile was sort of a double hump, a morning rush and a late afternoon rush. And under no delay, of course, the terminal occupancy peaks around those two rushes and has a fairly large recovery time in the middle. With moderate delay, that pattern sort of seems to hold, but as the delay becomes more and more severe, not only does your terminal occupancy increase significantly, but your recovery time and recovery magnitude are decreased, which leads to, again, more crowding and more possibility for airborne virus to spread. And you can see that reflected also in the total airborne virus in the departure terminal. One thing about this is it suggests that it's possible to come up with a concept of operations for real-time modeling. It could be enhanced by sensors in the actual data as people come in, so it doesn't have to be quite so approximate as this model does, but you could get a sense of short-term predictions of your terminal occupancy, terminal crowding, where the risk might be greatest. If you have some estimates of what you think your incoming infectious rate is, you could potentially estimate the total airborne virus that might be out there, and it would give you some time to act accordingly if you have some operational measures to combat this, reduce, virtual queuing, perhaps, for instance, to reduce crowding in various parts of the terminal. Okay, so let me summarize and talk about the next steps. So the operational response to COVID-19 was hampered by enormous uncertainty about transmission mechanisms, lack of models to explore the impacts of mitigations, and all of these things had to be done on the fly in real time as the impacts were becoming evident. So it was an enormously challenging situation. We created an approximate model with very low computational load to enable exploration across a wide range of operational conditions and behavioral assumptions to address uncertainty. So it's coarse-grained, it's approximate, but it enables us to compare a lot of different operational strategies against a wide range of parametrical assumptions for things that you just might not have very good information about, particularly things like the rate of incoming infections, perhaps early in a pandemic. And we illustrated the utility of the model through 2 experiments, looking at the impacts of load factor, the gate environment, and masking on transmission in both the aircraft cabin and the departure gate waiting area, and the impacts of ATC delay on transmission and departure gate waiting area. And I think we were able to identify some critical elements of operations and mitigations and trade-offs that can be built upon. So next steps, clearly the modeling and simulation can be improved in a number of ways. We can improve the estimation of the input parameters, prevalence, if we can get some guidance on that log normal curve that we use to determine the infectiousness, the emission rates of incoming passengers. That would be enormously helpful. We can refine the models for passenger behaviors, movement, and activities, and you've seen examples from talks earlier in this session that dealt with just that, and we would benefit from that sort of work as well. We want to extend the simulation to more dynamic phases of travel where you have queuing, security, customs queues. And again, you've seen an illustration of that from previous talks in this session. We'd like to link the simulation to study the effects of networks and flight itineraries on transmission. So can we apply this in a network model as a piece of a network model to assess the impacts of different itineraries and different network structures on transmission? And finally, we want to develop models for employee infection as well. It is a critical part of maintaining operations, both for the peace of mind of the people who are employees and frontline people who are keeping things going, and for their morale, and because it's kind of a moral imperative as well. Some of the applications of the model, we'd like to generate a large database of simulated results. First of all, to help us validate better and develop predictive descriptive model, mine the data for insights. We want to develop more concepts of operations for the use of the transmission model in operational planning and real-time operations. So there's sort of development of these pandemic playbooks, identification of best practice mitigations and possible cost benefits, 3 or 4 or 5 day planning for strategic events like holidays and things like that, and then real-time operations to respond to unanticipated disruptions of things like demand and capacity. Finally, we'd like to implement interfaces to other models and other processes. And again, I'll point back once again to the previous three papers that we saw presented here. There are all touch points among the presentations we saw here, and it would be really great to kickstart collaboration forward here so that we can get more comprehensive picture of the impacts of pandemics on air travel and the world in which it sits. Final thoughts. The COVID challenge was unprecedented in our lifetime. It's characterized by fear, uncertainty, lack of reliable data, lack of ground truth, and most importantly, and I think most tragically, a lack of consensus about what was going on and what to do about it. Restoration of demand, which is central to the aviation industry, requires a few things. It requires us to understand the impacts of COVID or any other disease dynamics and the mitigations that should be implemented. We need better data, and with data come need for privacy safeguards for situational awareness and response. We still don't have credible data about the number of infections acquired in flight. Those data just do not exist. And without those data, all our models are just models, and it's very difficult to build upon that. If we have these things, we can then formulate honest, consistent, and well-informed messaging, and that's critical to restore confidence. Hearing the cacophony that was often present in the early and even current phases of the pandemic, I don't think help restore public confidence in what's being done and in their own safety. Finally, there was a real false narrative, I think, that arose throughout the pandemic, and that is that public health and safety are in opposition. Public health and safety and business interests, I'm sorry, are in opposition. And if anyone understands that, the aviation understands that that is not the case. A robust aviation environment requires safety. It's fundamental. It's a fundamental principle in aviation. I think what was challenging here is that we're not talking about safety in terms of physics and aircraft performance. We're talking about safety in terms of public health, and it is a new and challenging domain. And I think that was part of what may have, I think, knocked the industry and stakeholders a little off the stride. Public health and individual risk assessments are coupled, but they are different. For illustration, I might be comfortable flying with a risk of 1 in 1,000 of contracting COVID. But if you multiply that by the 2 million daily passengers in the domestic American system, that's 2,000 new infections a day. And that may have public health consequences that are significant and maybe should be tended to. And if we don't address concerns of these other public health domains, they're going to impact all of us, right? Again, I may think it's safe to get on an airplane and travel, but if I'm going to travel to someplace that is an infectious hotspot, or if I'm going to travel to someplace where all the things I might want to do are closed because it is an infectious hotspot, I'm going to choose not to fly. And it's not going to be because I don't trust the aviation industry. It's going to be because of all of these other interconnected aspects that will influence my decision. So that's what I have. I thank you for your attention and open it up for questions.
Thanks, Rich. Yeah, very interesting talk. While we're waiting for questions to come in the chat, I thought your delay analysis was particularly interesting, and it was funny because you mentioned that whole misconception that public health and business interests are at odds, and it turned out that a higher load factor leading to lower delays and lower congregation in terminal areas was actually improving things. And so, the airlines would like higher load factor because it lowers their cost. So well, that clearly is not at odds.
Yeah, I would be careful. It doesn't
but what it did,
it relatively was less bad, but yes.
Right. Relatively
Understood.
less bad, yes. But what it did turn out, and there you might get an argument that, well, fewer people were flying, at the onset of the pandemic, and so there weren't as many delays. But we're seeing that the demand is starting to creep back up again, regardless. Even with all the safeguards in place, people are a little more comfortable and fairly fed up staying in one place. I know that I would like to be in New Orleans right now. In any case, what that did show is that the terminal area maybe is an area that is, or the organization and procedures around the terminal area maybe is something to look at. The way that Michael looked at the onboard, the loading and disembarkation, procedures, maybe there should be a little more organization procedure surrounding the terminal area organization, and that could help alleviate kind of these egress, ingress, flows. I know that a lot, so I know that it's very costly for them to expand the space, right? That is the one thing that they probably aren't going to do, but what they do with the space and how they organize people who are waiting for flights, it could probably be looked at. And I'd be interested to hear your thoughts on that.
First thought is you said it better than I did. Second thought is I was very excited to see Michael's work, because I think you're right on target that there's a great need and a great opportunity here to improve procedures that can alleviate congestion and alleviate bottlenecks in the terminal area. I think they're good anyway. I mean, just regardless of pandemic or not, but they become more critical under circumstances where public health and transmissible diseases are concerned. It was interesting as we were starting to do this work, there was a lot of work dedicated to safety in the cabin. There were computational fluid dynamic models. There were experiments with dummies spewing forth virus particle proxies and measurements. An enormous amount of work went into saying the cabin's safe, and look at all these modeling results. And there was virtually nothing about transmission in indoor spaces like shopping malls or terminals. I saw comments that flying is safer than going to the grocery store. Well, I didn't see anything about grocery store transmission. There was a really, and continues to be, a real dearth of ground truth data. One of the things I used in validating was a wonderful review study of 18 case a review of 18 case studies of suspected, of flights where there were known infected people on board and where they could, through contact tracing, assess highly probable transmissions. 18 total. And from 18 total cases, of which 9 had transmission, 9 did not. From that, we had to come up with some realistic estimate if our numbers were even within orders of magnitude. I'm not talking about 50%, 10%. I'm talking about factors of 10. And that situation's got to be fixed if you're going to get the kind of response and safety and confidence you need. I don't pretend to have an answer as to how it should be fixed, because it's a rat's nest, right? There's policy issues, there's technology issues. There were few tests early on in the pandemic, so I don't pretend to have an answer, but in planning for the next one, God forbid, we do need a better answer for this.
Yes. All right. I can only assume that we're not getting questions in the Q&A because everybody is rushing over to the plenary talk, which is again about the pandemic. This actually was this was actually a paper submitted, but it was so interesting and appropriate to to go across tracks that we made it a plenary instead of a paper. So it was kind of an upgrade. So yeah, up next at the top of the hour, don't miss the plenary by, I guess it's Mike Ball now and Mark Hansen, talking about the COVID-19 pandemic and US aviation. And they did a lot of interesting analyses on the, of the evolution of aviation data and the pandemic spread. All right, thank you for joining, and I'll see you over in the plenary.